Hi, for those of you who are big fans of learning intentions, if you go to the SQ website under course specification for advanced higher, you will find the two learning intentions that we're going to be looking at today in lesson 1 are at the very beginning of rotational motion in astrophysics. So we're going to look at number 1 here, the knowledge that differential calculus notation is used to represent rate of change. And we're going to be looking at the majority of learning intention number 2, the knowledge that velocity is the rate of change of displacement with time, acceleration is the rate of change of velocity with time, and we'll probably look at this this last bit will be looked at in lesson 2, the acceleration is the second differential of displacement with time. So don't worry about it at the moment. Okay, for the moment we're looking at this first one and the majority of the second one. Lesson 2 will cover the rest of the second one, and we'll look at the third one as well. Hello and welcome to Advanced Higher Physics, Lesson 1, Rotational Motion and Astrophysics. Well, what we're going to be looking at today is something that should be fairly familiar to you. We're going to look at the equations of motion. Now you might be thinking, well, equations of motion, did we not look at that at higher quite a lot? And the answer is yes. In fact, we looked at it at National 5 and higher. The only difference is this is kind of equations of motion, slightly amped up. We are going to the max on this one. Right, so at National 5, you should remember, hopefully, this equation here, this little equation. This equation is something you've been looking at actually since probably about first or second year of maths. And it's basically distance equals speed times time. It's a useful equation. It's one that works really, really well. But what we really didn't talk about at the time, because we didn't want to fry people's brains too much, is that actually this equation has a lot of limitations. We can only really use it when we have absolutely no acceleration whatsoever. If we have any acceleration, then there is no way that we can use this equation because the speed doesn't stay the same. So we can only use this as long as the speed stays the same. But that was fine for National 5. The other thing we could do at National 5 is we could do A equals V minus U over T. So we were allowed acceleration, and we could calculate the acceleration as long as the acceleration was absolutely constant. We could use this for a constant acceleration. If the acceleration wasn't constant, then there's absolutely no way that we could have used this one. Now, I'm going to borrow my daughter's pens here for a wee second. The key bit here is that we could not link at any point the distance to the acceleration. We didn't have any way of doing that. We could do a little bit of area under graph, and we did that a little bit for projectile motion, for the vertical height dropped. But other than that, we really dealt with problems where there's no acceleration whatsoever. At higher, we went one stage further. So at higher, we went to SUVAT. And as well as introducing this S instead of distance, because we had to use displacement here, it's important to use displacement because we had negatives and positives. You can't really use acceleration in these equations without taking into account negatives and positive. And we got the three equations of motion. S equals ut plus a half at squared, v squared equals u squared plus 2as, and v equals u plus at. Hopefully none of them should come as a surprise. Now in this case, there's also the fourth one as well, but we won't talk about that one. We could use this for cases where we had a constant acceleration. So this was okay as long as something was falling through the air and we ignored air resistance. So if it kept accelerating downwards, if we dropped a ball and it kept accelerating downwards at 9.8 meters per second squared, then that was fine. If we took into account air resistance, then it wouldn't constantly accelerate and that wouldn't work. So this worked in much more complex examples. It allowed us to do projectile motion, where a ball was going from one place to another. It allowed us to look at the vertical and the horizontal velocities and displacements. So it allowed us to do slightly more complex calculations. But unfortunately, not really any real world calculations. Real world was definitely beyond us because we couldn't take into account things that really happen. Objects that actually don't accelerate absolutely constantly. And that's basically most things. Advanced tire, if you're kind of following this, no acceleration, constant acceleration, you might guess what's coming up next. Well, advanced tire, we're looking at situations where acceleration is not constant. So we're looking at acceleration that might vary. And again, this can look at more real-world examples. We can have balls that are actually falling through the air, and where we actually have some air resistance, and as the air resistance increases, the acceleration is going to decrease until eventually, when the forces of weight and air resistance are balanced, we're going to have an acceleration of 0. We can actually now deal with these mathematically. Right, so how are we going to deal with these? Well, to do this, we need to use two mathematical concepts that I'm sure you know and love. We need to use differentiation and integration. The good news is we're not going to touch integration today, we'll leave that for a later date, but we're going to look a little bit at differentiation today. And we're going to start off back at the beginning again. We're going to start off with this equation here. Speed equals distance over time. Now I've done it in this way around because it's quite important to have it this way around to understand what's going on here. I think I'm going to maybe take it a wee bit further though. I'll take it to the kind of the harder end in Astro 5 and I'll make it displacement over time. Because from now on we are going to be using displacement. We really were at higher as well, but we really have to look at displacement here. It'll become clear why we have to use displacement, by the way, in velocities when we start looking at rotational motion. We're not just doing it to be awkward. So we've got our equation v equals s over t. But what does that actually mean? Well, what does a velocity of 2 meters per second actually mean in real life? Well, if you've got someone here and they're moving at 2 meters per second in this direction, then what that actually means is that every second they are going to be covering 2 meters. Or another way of putting it is that every second their displacement from the start point here is going to be increasing by 2 meters. And the way that we tend to put this in physics is we tend to say that actually the rate of change of displacement is 2 meters each second. So we can say that the rate of change of displacement, which is s, equals 2 meters each second. And the way that we express that mathematically, a rate of change, we can express, instead of saying v equals s over t, we can actually explain it as it's the change in displacement over the change in time. So for instance, this is a change of displacement of 2 meters in 1 second. This is a change of displacement of 2 plus 2, or well, no, actually in this case, sorry, 2 of another 2 meters in another second. So it's a change in s, so this will be 4 meters in total, in a total of 2 seconds, is the speed. Another way we can put that is that it is ds by dt. Because this is actually what ds by dt means, and hopefully they tell you this in maths. This means the rate of change, I know it's a differential form, but this is the rate of change of displacement with respect to time. And that brings us to our first formula for today, v equals ds by dt. The second thing that we're looking at today is another National 5 equation, a equals v minus u over t. It's actually easier though if I write it in a National 4 format, where I write change in speed, acceleration is the change in speed over the time it takes to change. You could actually say the change in time. You can probably see where I'm going with this. So if it's a change in speed, it's delta v, over delta t. Don't worry about this notation if you don't really like it very much. Remember we used it for a delta t at in National 5, cm delta t. Delta just means the change in. But basically the change in speed over the change in time, or the definition of acceleration, the change in speed per second, is basically the rate of change, and I should really say of velocity. Really, a National 5 level, that speed was okay, but to be honest, I should really say velocity back here. So the acceleration is the rate of change in velocity. The rate of change means the change per second, or the change in a unit time. And the way that we write that is A equals dv by dt. And this gets us our second equation here. If you're not sure about this, the other way of looking at it, and I'm sure you have done this in maths, is if we have a graph of y against x. And at this point here, we calculate dy by dx. dy by dx at this point gives you the gradient of the graph. It gives you the gradient of the tangent to the graph at that point, but it's the gradient of the graph at that particular point there. dy by dx gives you the gradient. So if we basically just change the letters and make this into a speed time graph, the gradient of this speed time graph, and it can be a straight line or it could be a curve, the gradient of this graph here is going to be dv by dt. So y here becomes v. X here becomes t. And as we know, the gradient of a speed time graph is the acceleration. So that brings us quite nicely to the second way of looking at this, which is that A equals dv by dt. It's the gradient of a speed time graph, or a velocity time graph. So the two things that you need to take from today are these 2 points here, that the speed can be expressed as ds by dt, and the acceleration can be expressed by dv by dt, and these are both the rates of change. So the velocity is the rate of change of displacement with respect to time, if you want to put it that way, and the acceleration is the rate of change of velocity with respect to time. They're almost always with respect to time. Coming back to the SQA documents again, I've done a few